Hey chemists, welcome to another episode of the chemistry edition of Last Minute Science, the chemistry podcast that's helping you get ready for your A-level exams. So today we're going to be diving into what is, in my opinion, one of the biggest foundational topics in all of AS chemistry. If you couldn't have guessed, it's bonding. So let's get right into it. Bonding. And this is such an important thing to study because it sort of shows up everywhere throughout chemistry. You know, you have these giant lattices, molecular structures, boiling point, solubility, you name it, it's there. If you understand bonding properly, so many other areas of chemistry just start to make that a little bit more sense, right? So it's a good foundation for us to start with. So let's kick things off with the big question. Why? Why do atoms even bond in the first place? And the simple answer? It's for stability. See, most atoms want a full outer shell of electrons, and they'll either lose, gain, or share electrons to get there. And depending on how they go about this, we get our three main types of bonding: ionic bonding, covalent bonding, and metallic bonding. Now, ionic bonding is probably the first one you came across. It happens when a metal reacts with a non-metal. Our metal loses electrons to form a positive ion by donating them to a non-metal. The non-metal gains those electrons, and the charge from them forms a negative ion. These oppositely charged ions are then held together by electrostatic attraction. So our metals become positive, our non-metals become negative, and that key idea of negative and positive attract very strongly is what holds these bonds together. That's the key phrase that you want to include in your answers, by the way, this electrostatic attraction between oppositely charged ions. They love that. For example, take sodium chloride. Sodium, our metal, gives up electrons and becomes Na+, and chlorine gains these electrons to become Cl-. These ions then arrange themselves in what we call a giant ionic lattice, a very complicated sounding name for something that's super simple. So a giant ionic lattice, and that strong attraction throughout the lattice is what gives ionic compounds their high melting and boiling points. But, and this is important, they can only conduct electricity when they are molten or dissolved in water, when they've been melted or when they're aqueous, because that's when the ions are free to move. In solid form, they're locked in place in our giant ionic lattice. So that's a key point. Ionic compounds can only conduct electricity when they are molten or aqueous. So from there, let's move into covalent bonding, which is when atoms share pairs of electrons instead of transferring them. Now, this isn't typically in the spec, this little bit I'm going to tell you, but this is how I imagine it and how I understand it. Or at the very beginning at least, this is how it clicked in my brain. A valence electron is a fancy, very fancy name for an outer shell electron. So if you piece that piece of knowledge with our knowledge of what the prefix co means, covalent bonding, co-sharing between valent, the valence electrons. So a covalence bond is a bond where two things are sharing valence electrons, right? That makes sense. See, chemistry is all logic really when you get down to it. So covalence bonds usually occur between non-metals. So think of something like water. H2O, where hydrogen shares one electron with oxygen. That way, everyone ends up happy with a full outer shell. So essentially, hydrogen is putting one electron into the middle, oxygen is putting one electron into the middle, and both atoms gain an electron to create full outer shells, and so stability. But not all covalent substances are the same. Some form what we call a simple molecular structure, like water or carbon dioxide, where these individual molecules are held together by relatively weak forces. These substances usually have low melting and boiling points. However, others, like diamond or graphite, form giant covalent lattices, which are a completely different story. They've got strong covalent bonds throughout the whole structure, which makes them very tough, very hard, and gives them high melting points. So, looping back to covalent bonds, we've got simple molecular structures, like water or carbon dioxide. Simple, meaning that they have a lower boiling point and weaker forces. And then we've got giant covalent lattices like diamond or graphite, which have strong covalent bonds, which gives them high melting points. Now, a little twist on the covalent theme is what we call a coordinate or dative covalent bond. So this is a shared pair of electrons, the same as our covalent bond. The only difference is that both electrons in the bond will come from the same atom. So both electrons in the electron pair come from one atom rather than one from each. A great example of this is the ammonium atom, NH4+. The nitrogen atom donates a lone pair to a hydrogen ion, forming a bond. Just remember that when you're drawing this, show the donated pair with an arrow, pointing from the donor atom to the other. Now we've got metallic bonding. See, metals don't really want to gain electrons, and they're not really interested in sharing them either. So they tend to just lose them and form some positive ions for us, which are then surrounded by a sea of what we call delocalized electrons. So these electrons are free to move, and this is why metals are such good conductors of electricity. And because of the strong attraction between the positive ions and the sea of negative electrons, metals have very high melting points and very high boiling points too. The more delocalized electrons, the stronger the bond. That's why magnesium, for example, which contributes 2 electrons per atom, has a higher melting point than sodium, which only contributes 1. Here's where things get a bit more nuanced. Electronegativity and bond polarity. See, not all covalent bonds are created equal. Some atoms are better at attracting electrons than others, and that's what electronegativity is, an atom's ability to attract a bonding pair of electrons in a covalent bond. Electronegativity increases as you move across a period and up a group. So fluorine is the most electronegative element, followed by oxygen, and then nitrogen, and then chlorine. When two atoms with different electronegativities form a bond, the electrons are pulled more towards the electronegative atom, creating what we call a polar bond. When two atoms with different electronegativities form a bond, the electrons are pulled more towards the more electronegative atom, creating what we call the polar bond. Take, for example, hydrogen chloride, HCl. Our H has a lower electronegativity than Cl, so the shared electrons are pulled much closer towards the chlorine, making that end delta negative. The prefix delta just means a little bit. It's slightly. It doesn't have an overall negative charge, but because the electrons are more leaning towards it, it's slightly more negative when related to the hydrogen. So chlorine is delta negative, and the hydrogen end, by process of elimination, would be delta positive. So this probably leads us quite nicely into intermolecular forces, which are the forces between molecules, not the bonds holding them together. So they're the interactions holding molecules together in a substance, which is annoying because one of the three types has bonding in the name, which I feel throws a lot of people and definitely threw me for a while. But you've just got to keep in mind that they're not bonds. They're just forces. So we have three main types of intermolecular forces, and every molecule has at least one. The first and the weakest are what we call induced dipole-dipole reaction, or induced dipoles. These are temporary dipoles that occur when the electron cloud around a molecule shifts slightly, creating a short-lived delta positive and delta negative end due to electron uncertainty. Even though they're weak and only temporary, they're important, and they're stronger in larger molecules with more electrons. These forces are present in every single molecule. Regardless, that's a key point to remember, because electron uncertainty is the case in every molecule. Next up are permanent dipole-dipole interactions. You can probably guess where this is going. If induced dipole-dipoles are only there some of the time, due to electron uncertainty, then permanent dipole-dipole interactions are going to be there all of the time. These occur between molecules that have permanent polarity. So in something like hydrogen chloride, the slightly positive end of the molecule is attracted to the slightly negative end of the other. These are stronger than induced dipoles, but still weaker than the last type of intermolecular force we're going to talk about, and this one is the confusing one, because hydrogen bonding has bonding in the name, which does not make it very easy to distinguish it from being a bond, because it's not. Hydrogen bonding is basically let's say like a supercharged version of dipole-dipole forces. Hydrogen bonding is like the big, strong, mean big brother of the intermolecular forces. And it only happens when hydrogen is bonded directly to either nitrogen, oxygen, or fluorine. Can you guess why? Because they're the three most electronegative elements. These bonds are super polar. And the hydrogen ends up with a strong delta positive charge that's attracted to the lone pairs on the other molecules. This is what gives water its high boiling point and makes ice actually less dense than liquid water. It's thanks to its hydrogen bonded structure. So, those are intermolecular forces. Now let's talk about shapes of molecules, because the type of bond and arrangement of electron pairs also affects our molecular geometry. And the theory you want here is that electron pairs repel each other and arrange themselves as far apart as possible in three-dimensional space. Just a fair warning here, shapes of molecules are probably the hardest thing to interpret without visuals. I struggle to interpret it without watching YouTube videos on shapes of molecules, so I'll go and link some of those in the description for you, and you can all go and take a look at those. I found people like Elliot Rientool to be very helpful when you're revising something like this. But I'll go through the theory anyway, and then if you're still confused, go off and have a look at some other videos and do some exam questions. So, the shape of a molecule depends on the number of bonding pairs and the number of lone pairs around a central atom. So, I'll just give you a few essentials to get you started. So, for example, if we have two bonding pairs, they will repel each other equally, and we'll get what we call a linear shape, which takes 180 degrees. For example, carbon dioxide. Something like three bonding pairs will give us what we call trigonal planar, trigonal triangle or three, and planar in a two-dimensional space. So each angle will be 360 divided by 3, 120 degrees, like BF3. Four bonding pairs we call tetrahedral, and this is our first 3D shape, and it takes 109.5 degrees. For example, methane, CH4. For three bonding pairs and one lone pair, you have to remember that a lone pair repels more strongly than a bonding pair. So I'll say that again. Lone pairs repel more strongly than bonding pairs, and they repel more strongly by about 2.5 degrees. So the key difference here between four bonding pairs and three bonding pairs and one lone pair is that our angle of 109.5 degrees from four bonding pairs, tetrahedral, has gone down by 2.5 degrees because of that lone pair. The lone pair is repelling the bonding pairs more than the bonding pairs repel each other. So we'll have about 107 degrees. For example, ammonia, NH3. And two bonding pairs and two lone pairs is what we call bent or V-shaped. And that's about another 2.5 degrees down, so approximately 104.5 degrees. Like water, H2O. So just remember that lone pairs repel more strongly than bonding pairs, so they squeeze the bonding angle slightly. Alright, that just about wraps up our tour through AS level bonding. We've covered ionic, covalent, metallic bonds, coordinate bonding, electronegativity and polarity, intermolecular forces, and molecular shapes, but only briefly. Again, I will put some videos down in the description that you guys can go and take a look at. Any works linked in the description are completely original, I'm not related to, and it's not promotional, but is just for you to go and take a look at because they're really useful resources. So, honestly, mastering this topic is like getting a key into the secret chemistry map, because bonding is literally everywhere in A-level chemistry. And if you found this breakdown helpful, consider reviewing the diagrams alongside this episode, especially dot and cross diagrams, shapes of molecules, and examples of intermolecular forces, because it helps lock the visuals into place. Anyway, that's all from me, and until next time, keep revising, keep asking questions, and remember, chemistry is not just about memorizing these random facts, it's about understanding patterns. See you all in the next episode.